In this video, I'm going to continue talking about unitless measures of association for linear regression models or effect sizes. But now I'm going to show how to do some of these things in R, continuing, well, in the last video, I didn't actually get to the code shown on the screen. So now we're continuing with the code shown on the screen. And the first thing that we're going to do is prepare a temporary data frame to avoid missing value problems. Missing values can trip you up when you're using statistics like the mean and standard deviation of a variable to help with your statistical modeling, which of course we're going to need to do for things like standardized slopes, because you don't want to accidentally compute those statistics using extra participants who have missing values on some of the other variables in your model. For example, if we have a participant who gave a rating for the robot's price, but did not give a rating for how fun the robot is, and we're going to use how fun the robot is to predict the robot's price, we would not want to include that participant when we calculate the mean and standard deviation of price for the purpose of z-scoring it or creating a standardized slope. So let's make a new data frame that has only the variables that we're planning to actually use for this example. And in this case, I'm going to focus on using the 3 different subjective ratings to predict the estimated price of the robot. So participants' ratings of how fun, practical, and cool each robot is, predicting the price that they'd be willing to pay for it. I'm using the square brackets here to create a copy of the robot's data frame. This is the original robot's data frame, and square brackets allow me to do subsetting. Before the comma is which rows I want to include, leaving that part blank includes all the rows. After the comma is which columns I want to include. I'm allowed to have line breaks in the middle of the line of code. The point of that is just to keep it all visible on the screen when I was writing the code, which obviously the console here is wide enough to display the whole thing, but when I wrote this, it wasn't like that. So the columns that I'm keeping are price, the rating of how fun the robot is, practical, and cool. These strings are being combined together into a vector using the C function so that they will represent a single vector, and then R will know to include the columns whose names correspond to the values in that vector when it takes the subset of robots. And the closing bracket ends the process of subsetting. And then I assign the result of that operation to a new object called robot_ratings, which is just the name of the data frame I'm going to use for these examples. The next step is to remove all missing values from that new data frame. You can easily remove all missing values from a given data frame by using the complete cases function before the comma in the square brackets for that data frame. So here I'm taking another subset, this time of the robot ratings data frame. And after the comma is blank. I'm keeping all the columns, but before the comma, I've got this complete.cases function call. Complete.cases gives a vector of trues and falses, where the trues correspond to the rows in the data frame that have no missing values, and the falses correspond to the rows of the data frame that have any missing value anywhere. So you wouldn't want to do this if you were working with like the entire robot's data frame, because then maybe it would exclude someone who had a missing value on some variable that you don't care about anyway, or a column that's entirely missing values or something like that. But here we've restricted the data frame just to these 4 columns we're actually using for modeling, so it's fine to exclude participants who have any missing values at all, and store the result in robot_ratings, overriding the original robot_ratings data frame. So let's start by looking at the regression model that is going to be sort of the background information for the examples of unitless measures of linear association that I'll be talking about here. I'm going to call this model mod_ratings, and it's the result of assigning the output of the LM function with this formula. Price is the response variable, the tilde separates it from the predictors, and there's 3 predictors: the rating of how fun, practical, and cool the robot is. And all those variables come from this data frame robot ratings, which is the result of me having removed all the missing values for those 4 key variables that I'm using here. And then I'm looking at the summary of this mod_ratings object. And as expected, we get a typical regression model summary, and that has an intercept and 3 slopes representing the slope for the rating of how fun, practical, and cool the robot is, all adjusting for each other, so they're being included simultaneously in this regression model. The first thing that I want to show you using this regression model is standardized slopes. And I'm going to compute them in three ways. First, I'm going to compute standardized slopes by standardizing or z-scoring all of the variables. And I'm going to use this scale function. The scale function standardizes or z-scores a variable or a set of variables. So when I apply it to the entire data frame robot underscore ratings, the result is a matrix of standardized values from that data frame. Then I convert it back to a data frame and assign the result to z underscore robot underscore ratings. So for example, here's a histogram of the price variable from robot underscore ratings. It's in units of dollars. And here's a histogram of the price variable from z underscore robot underscore ratings. This one is not in units of dollars. It has a mean of 0, and it has been constrained to have a standard deviation of 1. So it's the same distribution. It's just been shifted over so that it's centered at 0 and squished down so that its standard deviation is 1. This is the result of the z-scoring or standardizing operation. And this has been done to all 4 of our variables, not just price. So now I can fit a linear regression model with price as the response variable and our 3 predictors of interest coming from this data frame, z underscore robot underscore ratings, instead of the original robot underscore ratings data frame. So these versions of all 4 of these variables have been standardized or z-scored. And here I'm not looking at the summary, I just let lm print directly to the console. And when you do that with the linear regression model object in R, it just gives you the information about what the formula was and the coefficients for the intercept and the 3 slopes in your model. And the result here is these standardized slopes. We can ignore the intercept. First of all, remember I said that when you fit this regression model, the intercept is going to be 0. You don't see it written as exactly 0 in R due to rounding error, but -1 times 10 to the -16th is 0, basically 0. But these are the slopes, the standardized slopes for each of the predictors. And because the intercept is written in scientific notation, these are all written in scientific notation too. But e minus 0.1 or times 10 to the -1 just means move the decimal point 1 space to the left. So the standardized slope for rating.fun is 0.23, for rating.practical is 0.29, and for rating.cool is 0.34. These were the unstandardized slopes up here, and these are the standardized slopes. That's one way to get standardized slopes. We can also compute a standardized slope for an individual variable, or all of our variables, by scaling them appropriately. We're going to use standard deviations to scale these slopes. So mod underscore ratings is our actual slopes for these 3 ratings predicting price. And we can look at the coefficients part of that object by using $ coefficients after it. So this is just the portion of the mod underscore ratings that contains this vector of coefficients. And I can retrieve the coefficient for just the cool rating by using square brackets to subset this vector. And I want the element that has the name rating.cool. And that gives me the slope for rating.cool, 7.21. I could have also just typed 7.210167, but this way I get it directly from the model output, so I don't have to worry about rounding or anything like that. To calculate the standardized version of this slope, all I need to do is multiply it by the standard deviation of the rating.cool variable itself, and then divide it by the standard deviation of the price variable. So here I have done that. I have the cool coefficient extracted from the model object times the standard deviation of rating.cool from the robot ratings dataset divided by the standard deviation of rating of the price variable from the robot ratings dataset, and I get a standardized slope of 0.34, 0.33999. And here, the standardized slope was 0.34. Remember, this is 3.4 times 10 to the -1. So these two methods give me the same standardized slope. They're just 2 different ways of obtaining that slope. I'm going to show you a third way of getting the standardized slope using my standardized.slopes function. This is in a set of functions that I've called MISC functions. Maybe I'll come up with a better name later. But I have that set of functions in a file called miscfunctions.r in the working directory that I'm working in right now, just like I had makerobots.r in this working directory earlier. And by using source on that file name, I tell R to execute all of the code stored in miscfunctions.r, just the way I executed all the code in makerobots.r earlier. So I maintain this set of miscellaneous functions for general use, and you can get the latest version of these functions from my website. I'll keep updating it. One of the functions is called standardized.slopes. So I have mod underscore ratings, which is the regression model output from before, the regression model object from before, and I can call the standardized.slopes function on it, and it automatically gives me standardized versions of the 3 key slopes. So double checking rating.cool, for example, we've got 0.3999, just like when we manually calculated it here, and just like when we z-scored the variables up there. You can ignore the intercept portion. These slopes are found by adjusting by standard deviations and not by refitting the model with z-scored versions of the variable, so that leads to a different interpretation of the intercept, but it doesn't actually matter when we're talking about standardized slopes. Another function in my set of miscellaneous functions is regression table. So I can call regression table on this regression model object and specify a couple of arguments that I want confidence intervals and I want standardized slopes. And then I will get a table like this that has rounded versions of the slope, b, the standard error, the p-value, the lower and upper bounds of a 95% confidence interval for that slope, and the standardized slope. That's the same as what you would get by calling the standardized slopes function. So sometimes that comes in handy, having it in a table like that. As an aside, I can show you a couple other examples of miscellaneous functions from my set of functions. These are not relevant to the current lesson, at least I'm not using them in the current lesson, but there are examples of other functions in there that might spark your interest. So one is DES, which is short for like descriptive statistics, and you can get information about a numeric variable like price grouped by a categorical variable like color. It has many other options. This is just an example where we can see the mean price for the blue, green, red, and black robots and their corresponding standard deviations, numbers of valid observations, numbers of missing values, minimum, median, and maximum. This FREQ function for frequencies gives me information about a set of categorical variables in tabular format from this data frame, but you'll notice that price is not a categorical variable and it automatically groups price into chunks when you plug in a numeric variable like that. So here I might learn that in this bottom part of the price range from $39 to $65.40, I only have one blue robot, but 13 green robots. And, in this top portion of the price range, I only have a few robots in general, and so forth. And one more example, this e.plot function, which is a plotting function. You can use a formula or you can specify individual variables as the argument. And I've just, for the sake of example, asked for error bars with an alpha of 0.01. So this is a 99% confidence interval in this case. And we get a plot like this, where we have the colors on the x-axis and the material in a legend here. So the solid black dots are metal and the open green circles are plastic. And the error bars represent a 99% confidence interval for each of these estimated means. Anyway, back to unitless measures of linear association. We just got through talking about 3 different ways to get standardized slopes. Now I want to talk about partial and semi-partial correlations. And so for the standardized slopes, I showed you my own function that calculates those things. For partial and semi-partial correlations, I'm going to use the functions from this package called ppcore. I'm going to attach that package using the library function. So now, because I already have that package installed on my system, I was able to do this, and now I have access to the functions that are in that package. You'll notice that it gave a couple of messages. One of them is that it had to also load the MASS package because it's required for the ppcore package. And another is a warning message that ppcore was built under a newer version of R. My version of R is a little bit out of date. I should update it, and I will soon. So before using the functions from this package, let's take a look at the example regression model again. Remember that we're modeling price on the basis of these three subjective ratings, and we get these three slopes. And maybe we would like to get partial or semi-partial correlations between price and each of these other variables, adjusting for the other two. To get partial correlations, all I have to do is call the pcore function, which is from the ppcore package, with the robot underscore ratings data frame as its sole argument. This assumes that the data frame you're supplying as an argument contains all the variables and only the variables that you're going to use for the partial correlations. So the result is that I get a table of partial correlations. For example, 0.26 is the partial correlation between price and rating.fun, adjusting for the other two types of ratings here. And 0.32 is the partial correlation between price and rating.practical, adjusting for rating.fun and rating.cool, and so forth. Let's look at an example illustrating what partial correlations are again. I'm going to store some residuals from a regression model predicting price. So I've called the LM function with price as the response variable and rating.fun and rating.practical as the predictors. I'm leaving out rating.cool, and I'm retrieving the residuals from that regression model object using the $sign. And the result is a vector of residuals that I'm calling residuals underscore price, because this is what's left of the variability of price after accounting for rating.fun and rating.practical. Then I'm going to do it again, but I'm going to make residuals underscore cool by modeling rating.cool on the basis of fun and practical and retrieving the residuals. And when I calculate the correlation between those two sets of residuals, I get 0.37. And if I scroll back up a little bit, I can see that the partial correlation between price and rating.cool, adjusting for rating.fun and rating.practical, was 0.37. This is just a way of illustrating what this 0.37 actually represents. Now let's move on to the semi-partial correlations. And before I show you the output, I want to remind you that semi-partial correlations depend on which variable is treated as the response and which as the predictor. So these matrices are not symmetric. Looking at the output here, you can see that the value 0.259 here is not exactly matched the value 0.228. The values in the row for price are the ones that treat price as the response variable. So 0.228 is the semi-partial correlation between price and fun, adjusting for practical and cool, treating price as the response variable and fun, practical, and cool as the predictors. And so this set of semi-partial correlations at the top of the table right here represents the semi-partial correlations that I would use as effect size estimates or unitless measures of linear association to go along with the linear regression model example that we're talking about right now. Let's focus on this one for a second. The semi-partial correlation for rating.cool is 0.336. And I just want to show you an example reminding you what semi-partial correlations are. Previously, I calculated two sets of residuals from models predicting price and cool using the other two ratings, fun and practical, in order to get an example of the partial correlation. Here, I'm reusing one of those to get the semi-partial correlation, the residuals from the model predicting cool, but I'm using the actual values of price directly from the robot ratings data frame, and the correlation between these two values is 0.336, just the same as the semi-partial correlation that we got from this function from the ppcore package.